The topics I selected to discuss in this project were coordinate measuring machines, thread and gear rolling, bending, injection molding, and open die forging. I'll begin by discussing coordinate measuring machines. These are tools that are used to measure workpieces. It is important to first discuss a little bit about engineering metrology. This is the measurement of different dimensions such as length, thickness, diameter, and others. Some instrument qualities that are important to take into consideration are precision, accuracy, and sensitivity. So what are CMMs? These are tools for engineering metrology that take in readings in 6 degrees of freedom. In order to be used, a workpiece is placed on the platform, which can be moved and rotated. Measurement can be taken by motion in the X, Y, and Z axis. A moving probe as well records measurements of the workpiece. It does so by measuring various points around the workpiece to create a 3D map. Probes can be tactile or not tactile, such as lasers. These have a very high sensitivity of 0.25 micrometers. Typical applications for these tools include inspection, correction, and geometric dimensioning and tolerancing. These machines are used to compare the data collected, which are the dimensions measured, to what the true dimension should be. So why do I like this tool? First off, it is efficient, it works very quickly, and the machine checks each part the same way to quickly determine if the part is suitable or if some changes need to be made in the manufacturing process. As well, there is more room for design. Since the machine checks the parts for geometric dimensioning and tolerancing, there are more accurate checks and less worry about precision and accuracy. More complex geometries can be designed. As well, I believe that more companies will be using tools like this in the future. Many companies are moving away from having a full staff, and many even aim for lights-out manufacturing, where they aim to have no staff at all and have an automated functioning workplace. Now let's discuss some capabilities and limitations. To start with the capabilities, this tool can measure for geometric dimensioning and tolerancing with very great accuracy, which is very useful during the manufacturing process. As well, these measurements are accurate and repeatable. Parts can be quickly inspected up to 10 times faster than manually, which causes decreased labor costs and less flawed parts produced. In terms of limitations, it is necessary to calibrate the tool often to make sure that there is proper data collection. As well, these machines are very expensive, upwards of $30,000, and some may be even as much as $250,000. These machines also need to be isolated from vibrations, usually from production equipment. Additionally, there are software fees, and they may take up much space, especially for bigger machines for bigger workpieces. Now let's get into the second topic, which is thread and gear rolling. So this is actually a cold forming process, which means that there is no heat applied to the initial workpiece. The threads are formed by pressure, no material is removed. The rods are either passed through dies that are flat or through rolling dies. So some major applications for these are screws and bolts, of course, which are typically used in many sectors, namely the automotive industry, aerospace, lighting, and more. Here we have just a quick little diagram demonstrating how this process works. In the top, you're able to see how these are made with flat dies, which move in one dimension to be able to apply pressure and create the threads. For rolling threads, the workpiece stays still as well, and the cylindrical dies roll to create the threads. As for why I like this machining process, for one, a strong product is produced, which could be very important depending on the application. As well, this process results in low waste, which is very important for sustainability. Lastly, in terms of design considerations, there are consistent parts that are made. We can look at the capabilities first. In this case, there is enhanced strength when compared to cut threads. This is due to work hardening, since the grain structure of the steel is kept the same way. As well, there is reduced waste, very high production rates, around 30 pieces per second can be created, and as well there is a long tool life. In terms of limitations, the workpieces are limited in shape. They are typically round pieces such as rods, and they are also limited in size. They cannot necessarily be too large or too small. Lubrication can be used to diminish defects, which also could add a little bit of cost. And as well, this is not always usable for hollow parts. Now for the next topic, we're going to get into bending. Bending actually forms important features in sheet metal parts, which are very commonly used in various industries. An external force is applied to a sheet metal part in order to form different bends to create various features. And there are actually various methods of bending for sheet metal parts. The two that I'll be discussing more in depth are V-bending and roll bending. So V-bending is a very common method. In this case, a punch and die are used in order to bend to an angle. Then roll bending is important to produce parts with curves. There is an effect that takes place known as the spring-back effect, where the angle will be larger than originally bent to. So some common applications of bending are mainly to create sheet metal parts, and these are commonly found in many industries, including the automotive, aerospace industry, as well as many household appliances. You are able to see a visual representation of how roll bending works. So why do I like this machining process? So for one, in terms of design, many shapes can be recreated, so it does give some flexibility in that sense. As well, there is a low cost, which can be beneficial, again, when designing, since this is something that needs to be taken into account. Lastly, skills in sheet metal allow for work in a wide range of places. The main limitations of this process are actually the potential of cracks to form based on which way the rolling is done. As well, the plastic deformation is always followed by elastic recovery, so it is necessary to bend past the angle needed in order to account for this spring back. There's also potential surface damage, limited thicknesses that can be worked with, equipment costs, and equipment operators should be skilled, which in terms of capabilities, this manufacturing process can create a wide variety of geometries such as flanges, hemming, and channels. As well, it is very cost effective with a very high production rate, which is quick and precise. There's also low waste with this manufacturing process. The next topic to be discussed is injection molding. For this process, plastic pellets are inserted into a machine, which then melts the pellets. The molted pellets are hydraulically pushed into a mold to create the shape. There is a controlled volume of material that enters the mold. Once the plastic is inside the mold, it either hardens or cures to form the produced part. The part is then ejected by ejector pins after opening the mold. There are many applications in which this is helpful. Toys is actually a big one, such as Legos, automobile parts, electric components, hand tools, and bottle caps. Here are two visual representations of how this process works. So why do I like this manufacturing process? So for one, there is freedom in design, since there are various complex geometries that can be created with this process. As well, there is a low-cost, mass-produced result. Lastly, plastics are widely used in many manufacturing applications. It could allow for work in many different areas. Let's discuss the limitations first. Ejector pin markings can show up on the resulting product. As well, plastics do have ethical concerns since they are not biodegradable and could cause further pollution to our planet. These machines are expensive, and a new mold needs to be created for each part. As well, molded parts shrink during cooling. Now, in terms of capabilities, this does have a very high production rate. It is around 5 to 60 seconds for thermoplastics. However, thermosets do need that time to set. Molds can have multiple cavities, which means that multiple parts can be created per cycle. As well, there are minimal finishing requirements, as well as low-cost product as a result. And there is a high degree of precision in creating these parts through this process, which is as well reliable and long-term. The last topic I'm going to discuss is open die forging. This is a bulk deformation process. So for this, metal is deformed between two dies, which are usually flat pieces or very simple contours. An applied force to the system results in deformation of the heated piece. The workpiece is typically cylindrical and should deform uniformly to form the flattened piece. Common applications of this process involved disc, rings, sleeves, shafts, which can be used in aerospace, energy, and automotive sectors. Let's start with the limitations. So in the actual process, barreling very commonly occurs, which is where friction causes deformation to not be uniform. In order to counteract this, heated dies or a thermal barrier can be used, which do result in added costs. Machining is often required as well, and this is not suitable for precise parts. In terms of capabilities, there is low tooling cost, at least compared to closed die forging, and there is less product waste. There are lessened costs in materials, and there are diminished setup costs, again when compared to closed die forging. This process can create short-run parts with straightforward designs and can create a wide range of size products. So why do I like this process? Well, for one, it can quickly produce very simple geometries. Lastly, many industries could utilize this process, so it is important to know.